before I start chatting too much more. Look at that timing. So, I only got a handful of responses for the things you want me to review, so I put those, and I also put the ones that I thought would be worth doing, things I think people may make a mistake on. The final is made. I have generated it, I've made the multiple versions. It's gonna be good. 40 questions, no free response. Roughly 4 questions from each chapter. A handful of them only have 3. Yeah, I don't even remember which ones exactly only have 3, but you probably won't be able to tell anyway which ones only have 3. They all kind of blend together. So I'm going to be working through these problems. These are the kind of ones I generated. This is on, apologies for the, I normally like to upload things well in advance, but alas, because I was working on the final, I just managed to get this done about 30 minutes, 50 minutes ago. So I've got some problems on there. I, of course, will upload whatever I scribble down today, whatever stuff I add, I'll upload the additional ones. My hope, though, is that this kind of irons out some of the more difficult stuff, helps clarify some of the things that will be on there, won't be on there. Anything that I'm doing in this problem solving, there's skills you'll need from this, certainly. I wouldn't waste time solving problems on it if it wasn't going to be relevant. So it's a good indicator that these types of problems are useful. What else was I going to mention? I will not have office hours next Tuesday, so I will not have office hours this next week because it's exam week, with the exception of Thursday. I'll have them for the 30 minutes or so before the exam because, well, 15 minutes or so before the exam, because I'll be here already. But Tuesday, we'll not have them. Other than that, I don't know too much more to say. I mean, it's the end of the class, you only made it. I mean, at this point, hopefully you're feeling good going into the final. If not, do the best you can, try to learn from the mistakes that you previously had, look over the solutions, general things. So, looking at, I can show the 5 responses. None of them identify anyone. They don't have names or anything. Oh, I got 7 now. Wow. So there's some right-hand rule stuff. Yeah, definitely we'll do some stuff with that. Combining series and parallel resistors, vectors, anything to go with vectors, wires in opposite directions, yeah, capacitors and resistors adding together. So I have all that stuff here. I have vectors, but the good news for you all is I am not going to have any vector problems where you need to use trigonometry. So there's no vector problems where there's an x and a y component. The only vector problems I'm going to have on there are going to be where they're opposite directions or same directions. The rationale behind that is at the end of the day, there was only in electric fields we see ones with vectors. I already asked some questions on that. So it won't show up on here, but you do need to remember that opposite directions subtract. You're going to see that today. There's going to be some problems today about that with magnetic fields and electric fields, and so anyway, hopefully that gives you a little bit of peace of mind. So let's start off with one of the problems of the last test, one of the response ones. This is not that problem because I didn't want to spend that much time. Remember, the problems that are going to show up in the final will not be as complicated as the free response from the last 2 tests, but they may be like a portion of them. So maybe similar in terms of the concepts you're using, but not as much calculation. So, for example, on the last test, I had a wire going this way, a wire going up, a wire going down, a circle, and then another circle, one of them going clockwise, another one going counterclockwise, and I said, find the magnetic field here in the center. This problem is a simplification of that. It's a piece of that. So that's kind of the idea you could expect. I have a wire carries wire, that doesn't make any sense. A wire carries current straight up. So, great. And a loop of wire located 1.5 meters to the right of this wire has a radius of 3 meters and carries current. Pick a direction, clockwise or counterclockwise, I don't care. Clockwise it is, good choice, good choice. Clockwise. Forgot to identify that here, but we do need that. 1.5 meters with a radius of 3 meters. What is the magnetic field at the center of the loop? So we'll call that point P. If both wires carry 3 amps. Now, some problems will have a picture. Some problems will not have a picture when it comes to the final. That is purposeful. Sometimes I give you a picture because I want to make certain it's clear what I'm asking and what I'm trying to describe, and it may have been hard to do so in just words. Sometimes I'm not going to put a picture because I want to test your ability to take words and generate an image from that. That is a skill in physics. In the real world, you don't always get to see what people are talking about. They talk about something, and you have to generate a visual model of what they're talking about. So both skills are important. This problem didn't give you, I mean, in this case, most of these don't have a picture because they also take a little bit to make. But this is an example of that. This one I probably would have given a picture because when I say located 1.5 meters to the right, that's maybe, is that to the right? Whatever. If I give you the words, I try to be as clear as possible, and at any point, if you all have questions about the wording I used during the final, please ask me and I can provide some clarification about where things are. So, here you go. We got our two wires. They both carry current, so our givens, let's call this one I1, let's call this one I2. So I1 equals 3 amps, I2 equals 3 amps. Radius of wire of the loop is 3 meters. And I'm going to kind of leave it here. We're going to have to introduce another variable, but I'm going to wait a little bit before I put that in here. What are we solving for? We're solving for the magnetic field at the center. So the trick to doing this type of problem is recognizing that each of these wires is its own thing. So at first, I'm going to pretend like this loop doesn't exist. I'm going to pretend like that loop doesn't exist and I just have a straight wire. So I need to find the magnetic field at that point due to the straight wire. Because I have two things and I need to figure out, so I need B net, which means B1 plus B2, where B1 is the wire, B2 is the loop. So B1 is going to be the wire, that's going to be mu naught I over 2 pi r. And then I'm going to need B2, that's due to the loop, that's mu naught I over 2r. Equations look almost identical. The way I remember the difference between these is a loop is more powerful, and so it's missing that pi on the bottom. It makes a stronger field because all the pieces are kind of helping each other more, whereas the wire makes a weaker field, so you put a pi on the bottom that weakens it. Helps you remember. You'll have it in a note card, so. And at this point, we can calculate those. We do need to determine the direction of them. So, do they add? Do they subtract? We do need to realize that. So we use our right-hand rule. Number 2. I have to go through my head. I don't remember the names. I remember from this class who used them. So let's do the straight wire first. And I'll give you all a second to try that. What's the direction of the magnetic field at point P due to the straight wire? All right, what do y'all think? Up, down, left, right, into the page, out of the page? We got a cozy classroom today, so. Into the page, let's find out. Thumb up, finger towards point P, your palm points the direction of the field at that point. So yeah, point P is into the page. So into the page, we'll call that B1. All right, and then the loop, you can still use right-hand rule 2 and just pick a spot on the wire, any spot works. Or you can use right-hand rule 2.5. I'll do both. Let's just pick a spot here. Thumb up, fingers in the direction of P, and still into the page. Or I can curl my fingers around in the direction of the field. And you also get into the page. 2 ways to Sunday. And you can pick any spot on this wire. Thumb down, P is here, into the page. There's a couple different ways of doing this. But the end result is that they're both in the same direction. That's all we cared about. Are they opposite directions? Are they the same direction? Let's assign into the page as negative. Yeah, sure. Let's assign into the page as negative. I'm just going to kind of jot that over here. Into page, and we're going to say that's negative. Out of page, positive. It doesn't, the only reason I think this is useful to do is it'll help us see that we're adding 2 negative numbers. All right, Now, if we look at our equation, before we just start plugging in stuff, we're basically there. Let's double check that we have everything we need. We have I, we have mu naught, we have big R. We do not have little r yet. We haven't written it down. Little r is the distance from wire 1 to the point that we care about, which if we look at this picture is the 1.5 meters plus the 3 meters. So R1, let's call it that, equals 1.5 plus 3. It's the distance from the wire to the point we care about. Comes out to 4.5 meters. So that is a skill we need, is being able to take a couple pieces of information and generate a new variable. So at this point, I'll make a new slide. It's just plug and chug at this point. This last step is the least interesting, and I don't know. Maybe the calculator part. I almost want to say the least challenging. In my opinion, once you've done steps 1, 2, and 3 correctly, step 4 is just putting it all together. And it's just really being careful with your calculator. So B net's going to equal, and remember we defined into the page, so these are negatives now because we defined into the page as negative, 2 pi R1 plus negative, again, just putting that negative to make a point. That's the reason I'm doing it. Make a point that these are both negative because they're both into the page. We decided that's negative, so equals, I tend to pull out constants at this point just to make my life a little easier plugging it in. So I tend to do this. You don't need to do this. I just find it makes my life a little easier when plugging variables into an equation. Pull the negative out, 1 over r. Whatever. You don't need to do that. I simply do that because I don't want to have to plug in 4 pi times 10 to the minus 7 twice. But honestly, I'm just going to write out the math here as if I didn't do that. I'm just showing you all that that is a technique that just saves you a tiny bit of time. Less button presses on a calculator. So I'll put that off to the side just to show you can do it, but at the same time not really worry about it. And again, this is the least exciting part. This is the most, yes, this is what's going to determine whether or not you get the right answer because it is multiple choice and you're either wrong or you're right. But the beautiful thing is you can't get one of my answers unless you plug it into your calculator correctly. So that's a nice thing with multiple choice questions is if you plug all the stuff in your calculator and you get an answer that's not there, either you plug stuff wrong into your calculator or you did it wrong. The nice thing is they kind of, multiple choice tests kind of check your work for you in some ways as far as calculators are concerned. So if you do make a calculator mistake, it'll tell you because your answer choice won't be on there. Just will not exist. All right, so I get, and I'm double checking that I plugged everything in correctly because that was a bunch of numbers to plug in. Okay, I get negative 4.95 times 10 to the minus 7. And we do have to remember our units. That's Tesla. Now, at this point, what you could do is two ways. So I'm not going to have any answers on the test. When it comes to vectors, there's no positives and negatives. When it comes to vectors, my answers, if I'm asking you for the magnitude and direction, my answers will be 4.97 times 10 to the minus 7 into the page. Or 4.95 times 10 to the minus 7 out of the page. Or up or down or whatever. Nowhere on the test will positive mean something or negative mean something. It'll be in words, the direction. So in this case, if this was a question on my test, the answer would be 4.95 e to the minus 7 into the page. If I asked for the direction and the magnitude. And this is the hardest problem this is the hardest type of problem you could expect on This is the ceiling for difficulty. You will not experience a problem more challenging, more complex than this. This is the ceiling, so maybe let's see, how many problems could I say have this? Somewhere between 5 and 10. Not that many probably in terms of this difficulty, maybe 5, 6 out of all 40 of them. Everything else will be simpler than this. But this is a two-step problem. You had to find the magnetic field of both of them. You had to know whether to add or subtract them. And then you also, had to be able to determine the direction. But that came throughout all of it. Cool. All right. So again, worst case scenario. So that's the magnetic field version of this problem. Two wires of different, in this case there were different types, but I could make 2 loops, or I could do 2 straight wires. At the end of the day, this problem boils down to I have 2 things that make a magnetic field, find their contributions at some point, figure out whether you need to add or subtract those. This problem is the electric field equivalent of that. This problem is the electric field equivalent of that same problem. In the case of electric fields, it's not due to currents, it's due to charges. So I have 2 charges located 5 millimeters apart on the x-axis. Q1 is on the left, Q2 is on the right. If Q1 is 3 nanocoulombs and Q2 is 5 nanocoulombs, find the magnitude and direction of the electric field 1.5 millimeters to the right of Q1. A lot of information here, and that's why whenever you see a problem like this, and if I don't give you a picture, your first step should be to draw a picture so you don't have to read this information every single time you want to figure out what's going on. Drawing a picture just makes your life so much easier. So, Q1 is a positive 3 nanocoulombs. And in fact, I'm not going to write nanocoulombs because I'm not going to plug that in my calculator. I'm going to put 3 e to the minus 9. So that's Q1. My goal with the picture is to never have to read the problem again. By drawing a picture, I should have everything I need, so I don't even have to read the problem, read the words again, and you have a nice picture that shows everything. I have Q2. These are both on the x-axis, just meaning they're lined up with each other. Q2 equals 5 e to the minus 9 coulombs. And I say they're located 5 millimeters apart. So this little distance here is 5 e to the minus 3 meters. So that's most of our picture. The only thing we're missing is where are we finding, it says find the magnitude and direction of the electric field at some spot that is 1.5 millimeters to the right of Q1. So I'm going to pause, let you all try to figure out where that spot is. See if you get the right spot. Because if you pick the wrong spot, everything else is going to fail. You won't be able to get the right answer. Where is this spot located in this picture? Alright, so it says it's to the right of Q1. Well, there's Q1. We go to the right of it. How far do we go to the right? 1.5 meters, which if the distance between them is 5 millimeters, it's not the full distance. It's going to be closer to Q1. That's our point. Right there. Which is 1.5 e to the minus 3 meters away from that. So this, in my opinion, is the hard part of the problem. Drawing the picture, because if you mess this stuff up, everything else falls apart. And so really this question is testing 2 things. It's testing your ability to take some words and generate a picture from it, and then it's testing the content. So again, this is kind of the ceiling of difficulty. Like the last problem, this is as hard as they get. So if you're looking at this, like, is every problem going to be like this? No. 5 to 7 problems out of the entire thing. And these 2, I don't know, depending on your perspective, then maybe this is like the hardest problem that'll show up in the quiz kind of thing, if there's, or to find out if there's something like this. So we have our point. Let's go ahead. We already have all our givens kind of written down here. I'll make my own little list just to maybe make it a little easier to read. Q1 is 3e to the minus 9. Q2 is 5e to the minus 9. And I'm going to leave it there for a second, and then we'll come back to step 1 to see what variables we might need. Sometimes I know what variables we need here, but just to show you all, if you're ever stumped, don't just stop here. If you're like, okay, I only got 2 things, what else do I do? Try moving on, and when you get to the equations, that can sometimes reveal the variables that you may need to find in the picture. So that's what we're going to do here. What are we solving for? We are solving for the magnitude and direction of the electric field. We're trying to find the net electric field. Why net? Because there's more than one. It's not just the electric field due to one of them, it's the electric field due to both of them together. So towards that end, we're going to need to add up the contributions of E1 and E2. And I use the word add here very hesitantly. We need to figure out whether to add or subtract. For now, we'll just say add, and then we'll assign directions and plug those in later. We'll say to the right is positive, to the left is negative. Same old, same old. And our equation for electric field is going to be KQ over R squared. Do not forget the squared. And so at this point, we look at our equation, we say K, got it, 9 times 10 to the 9. Q, got it, for both of them. One of them is 3e to the minus 9, the other is 5e to the minus 9. E2 I don't, or R, I haven't written down yet. So what is R? It's the distance from the point, from the charge to the point. So in the case of Q1, real easy. R1, let's go ahead and put that there now that we've realized that we need it. R1 is the distance from charge 1 to the point. So R1 is going to be 1.5 e to the minus 3 meters. Great. R1 done. What's R2? R2 is the distance. Let's make that one a different color of blue. It's the distance from the other charge to that point. And this one requires just a tiny bit extra work. Nowhere on the picture does it have that value already. We have to recognize that the distance between them is 5 times 10 to the minus 3. Then I'm going to subtract. I'm going to do 5e to the minus 3 minus 1.5 times 10 to the minus 3. Because I am trying to find this blue line, I know this big distance between all of them. I know the distance from one to that, so you subtract this too. 3.5 times 10 to the minus 3 meters. Okay. The only thing left that I want to add to our picture is I want to add the direction of the vectors to determine if we add them or subtract them. I'll give you all a second to figure out which way does the electric field point at point P due to each of those charges. I'll let you all think through that and see if you can draw them in the right direction. Give you all a moment. We got time. Do they point in the same direction and therefore I add them, or do they point in opposite directions and therefore I subtract them? So here we remember that the electric fields point away from positive charges. So this point P here, the electric field due to 1 is going to point that way to the right. The electric field due to 2 is going to point the other way, and I sadly don't quite have enough room for that. Shift this over. The electric field due to 2 is going to point the other way, because it points away from the other one. Electric field points away from the charges. So in this case, let's define E1 as positive. Let's define E2 as negative because it's pointing to the left. So at the end of the day, what's actually going to happen is our E net's going to be E1 plus a negative E2. You have to do that step when it comes to these vector problems. And the beautiful thing is step 4 is actually fairly simple at this point. So E net is going to equal K times 3e to the minus, well, I'll put the value of K. That is, well, let me make things nice. So E1, let's put all the variables, K, Q1 over R1 squared plus a negative K, Q2 over R2 squared. Plug and chug at this point. 9e to the 9 times 3e to the minus 9 over 1.5e to the minus 3 squared plus negative 9e9 times 5e to the minus 9 divided by 3.5e to the minus 3 squared. Don't forget that squared. That'll kill you on these. So all the hard steps were really just drawing the picture, where's the point, and then finding out do the electric fields go in the same direction or opposite directions. We define to the right as positive, as is convention, and we define to the left as negative. All right, plug a whole bunch of things in our calculator and then double check that what we plugged in is correct. And we get a very large magnetic field, or a very large electric field here, because the distance is quite small. Nanocoulombs may seem quite small. Oh, I just plugged that in. So we're getting a big answer here because we're squaring that distance, which is quite small. So, 9 nanocoulombs may not seem like that much, but then you remember that electrons are times 10 to the minus 19, so that's 10 orders of magnitude bigger than an electron or a proton. So, evens out. So we get 8.33, let's go to 2 decimal places, times 10 to the 1, 2, 3, 4, 5, 6 newtons per coulomb. And we got a positive answer. So that tells us which way it's pointing. It's to the right. Positive we defined as to the right. To the right. And at any point, if what I'm doing doesn't make sense, these are great problems to go back and practice. Do not look at the solutions while you're practicing. Look at the problem without the solutions first. See if you can draw the picture right. See if you can go through it. Only look at the solutions when either you get a final answer and you want to check the final answer, or if you get really stumped on a step and you need just the next step. If you work on these problems with the solution open, you're not practicing in a way that will match what the final is going to look like. You're not going to have the solutions to the problems on the final. So you need to be able to solve the problems as much as without looking at the solution as possible, but use it as a tool. Use it as a tool with the recognition that at the end of the day, after using the tool, you should be able to solve this without looking at it. All right, so there you go. Okay, one of the hardest problems, in my opinion, these top two are probably the hardest ones I have in here. Good news, if you're looking at these and you felt like you knew what was going on, you felt pretty good about it, great. You're going to do awesome. If you're looking at these and you don't know what's going on, great. Practice them. They're available for you all to kind of go through and practice. And then again, this is the worst case scenario. Pretty much most of the problems I'm going to be doing today are the harder problems. I will throw in a couple of ratio ones at the end because I didn't include those yet. So pretty much all of these are going to be kind of the top tier difficulty. Not to scare you, but because that's probably what's worth spending the time on. And if you can do these problems, you can do the easier problems. It's also the logic. So let's go ahead and jump to this one. 2 wires carrying current and finding the force per unit length in them. This was a question that was on the last test. So I have 2 wires, 3 millimeters apart, and they carry a current of 2 amps. So there's my 2 wires. What is the magnitude of the force per unit length of one wire and the other, and will they attract or repel if current's in the same direction and current's in opposite direction? So there's our same direction, there's our opposite directions. It doesn't matter if one's up and one. It doesn't matter if I draw the left one going down. It didn't matter if I drew them this way. It doesn't matter if I draw them this way. All that matters is that these are 3 millimeters apart, 3 e to the minus 3 meters, 3 e to, and that they both carry 2 amps. When it comes to this problem, I'm not asking which way will they move, not like up, down, left, right. I'm saying will they together or apart? So, givens I1 equals I2 equals 2 amps. The distance between them, let's call that R, is 3 e to the minus 3 meters. Step 2, we are solving for F over L, force per unit length. We've seen that in quite a few problems at this point. Not force, force per unit length. It's different. You can't solve for force. You don't have the length of the wire. So you'll quickly, when you're solving this problem, realize you can't even do force. So F over L equals just IB. IB. Current of the wire experiencing the force and the magnetic field due to the other wire. So, I say the force of 1 on 2, then it's a current 2 due to the magnetic field 1. Vice versa. It doesn't matter which one you do. Newton's third law for every force is an equal and opposite force. It's multiplication. So it ends up, you'll see that when I plug in the variables, so the magnetic field due to a current carrying wire is mu naught I over 2 pi r. So if I just plug in the numbers here, I get current times mu naught current over 2 pi r. It's multiplication. Who cares which current you put where? Works out the same. In this case, they both have the same current as well, so double easiness there. But if I made 2 and 3, or 5 and 10, 5 times 10 is 50, 10 times 5 is 50. Order doesn't matter. So, solving for the force per unit length here, pretty straightforward. Not too much challenge here, honestly, on the last test. We all did a pretty good job of calculating the value of it. The challenge, the mistake that people made, if they made a mistake, no, good amount of people got it right, but if you got it wrong, it wasn't in calculating the number, it was in calculating whether they attract or repel. And the beautiful thing is, the answer to do it, whether they attract or repel, is just a rule. I'm going to show you all how to get it, how to work through it. But even before that, I'm just going to I'll tell you right now. If they're going the same direction, they attract. If they're going opposite directions, they repel. Done. Always. No. Straight up tell you right now, if you don't know why, that's okay. I will explain why, but that's always true. So you can also just get by knowing that if they're same direction, they attract, and opposite directions, they repel. I will explain why that is the case after I get this answer. Okay. I got 2.67 e to the minus 4. That's a terrible E. Newtons per meter. If you got a different answer than that, feel free to call me out. At any point while I'm solving these, if you got a different answer than me, feel free to call me out. It's always good to double check your work. My hope is that, so for this exam, you all get 2 hours and 50 minutes, which is more than double our class time, and the test will have less than double the work as the last test. So my hope is that you all will have plenty of time, not only to solve the problems, but to go back and check your work. I can almost guarantee you that if you go back and check your work, you'll very likely spot one error, at least. That's based on my personal experience. Now, I will tell you, when I was sitting in your seat, when I took Physics 2 for the engineers, I remember at the end of an exam, that's the last thing I wanted to do was go back and do it. I wanted to just be done, and you're certainly welcome to just be done, but if you're willing to just if you got the time, go through it. Generally, I caught some mistake somewhere whenever I started implementing that practice. We're humans, we make mistakes. One of the strategies for avoiding that is double checking your work. And, pro tip, one of the ways you can double check your work is you can plug your answer back. In this case, maybe you can't plug it back in, but if you had to do some algebra, plug the answer you got back into the equation and see if it returns the other stuff. So we'll do that with one of these later ones. But that's a great technique for checking your answers. It should work if you plug it back in. In this case, we didn't have to do any algebra, so whatever. All right, let's go ahead and talk through real quick why they attract, why they repel. It's a good practice of right-hand rule 1 and 2, because you have to use both of them. So if we have two wires going the same direction, let's say that wire 1 is making a magnetic field here. And let's say, because it is. The question is, so wire 1 makes a magnetic field where wire 2 is located. Based on the direction of that, it will cause a force. So wire 1 makes a magnetic field, wire 2 experiences the force, or vice versa. So what's the direction of the magnetic field at this point due to wire 1? Good practice. Try it out. I'll give you all a second. I won't give you the answer right away. Direction of the magnetic field at that red dot due to wire 1. Alright, so we use right-hand rule number 2. Thumb in the direction of the current, fingers towards point B, palm points in the direction of the force, the direction of the magnetic field, which is into the page. So actually, can't put that dot here anymore. Need to change that to an X. And if you do we can just prove a point. Let's find the magnetic field here due to wire 2. Thumb goes up, finger towards the point. This one is out of the page. All right, now we do one case at a time. Let's find the force on wire 2. So we just pretend like this whole thing doesn't exist anymore. Find the force on wire 2 due to the magnetic field into the page. So this is right-hand rule number 1. Find the force on wire 2 due to wire 1. Do that. Due to magnetic field into the page. You basically pretend like this one doesn't exist anymore. You've already used that one for what you need it for. So we put our thumb in the direction of the current. Thumb goes up. Oh, sorry, did it wrong one. See, it's the right-hand rule. Fingers go up. Palm goes into the board. Thumb is in the direction of force. One of the ways that this may help you remember which right-hand rule is which is your thumb is really strong, and so your thumb goes with force. I don't know. Maybe that can help you remember which one's which. Sounds silly, but I just made it up right now. So whatever that's worth. So the force is to the left. It is attracted to the other one. If we do the exact same process for the other wire, fingers in the direction of this, hand leaves the point out because that's the direction of the magnetic field. My thumb points that way. And a good way to check your work here, well, they should be equal and opposite. Newton's third law should be true. You repeat the exact same process for the opposite wires. So the magnetic field due to wire 1 will be into the page for 1. The magnetic field here will also be into the page because my wire flips, my magnetic field will flip. If we do right-hand rule number 1, fingers point down, palm is into the page, you get a force that repels. So this is a good exercise in just practicing both right-hand rules. I really like this problem because it makes you use both right-hand rules. Takes two concepts and put it together, but there is the shortcut. If they're the same direction, they attract, opposite directions, they repel. You don't have to do all the extra work. You can add that to your note card. Doesn't hurt my feelings. But good exercise to practice your right-hand rules because it's got kind of all the pieces in it and it makes you use them together. Okay. Any questions so far? We never really have time to just pause. At any point, if you all have questions, we have a nice cozy room together, like, haul them out, raise them up, let me know. If you're ever confused about anything, have me pop. Like, we got the time. All right. Faraday's law. This is the last kind of use of right-hand rules. So I figured I'd put it here. And there's no picture. So again, helps you have to visualize that. A loop is flat on a page. So that means the loop right there. And a magnetic field that's pointed into the page. If the loop leaves the magnetic field, which way will current be induced? Try to draw a picture, y'all. Have a mental picture, have a physical picture, have something, try to visualize what do you think it's going to look like. Because if you don't know what this is going to look like, then yeah, you can't solve it. It's the nature of physics. Can't really solve most of the problems. And that's when I stopped enjoying. So at some point, physics gets so complex that I can't visualize what was going on anymore when I got to graduate level stuff, and I did not enjoy that. But for this lower level stuff, introductory stuff, it's the fundamentals. So we can always draw pictures. When it gets to quantum mechanics, you can't draw pictures anymore. It's devastating for some of the more complex stuff. All right, there's my loop. It's in a magnetic field that leaves the page, so that's a bunch of dots. And at some point, my thing leaves, and it no longer has those magnetic fields into the page. So, the rub of the trick to this, I want to oppose the change. Yeah. Yeah, thank you. Into the page should be X. Thank you for that. Fantastic. Good catch. So, we went from into the page to none of them. We want to oppose the change. We lost magnetic fields. We lost them. So let's imagine maybe we're not fully out of it, or we're somewhat out of it. Our thing doesn't want that. It's going to make some extras to oppose that change. It's going to make some into the page to oppose that change. Now that you all know that, which way is the current going to flow? And the question is, which way does current need to flow to make that happen? We use our right-hand rule 2.5. Put your thumb into the board. You get a clockwise current to make that happen. We need more into the page. We put our thumb into it. All right, next one. A loop's flat on the page in a region of no magnetic field. If the loop then enters a magnetic field, which is pointed out of the page, which way will current be induced? Same thing, try it out, see if you get the answer. I'll wait for a few moments. So we kind of have the opposite situation. We start nothing. And, you know, maybe off to the side of it, we have those magnetic fields pointed out of the page. Makes it a little easier to draw what's going on here. So it starts nothing, it's not enclosed by it, but then at some point later, part of it has some of that, or all of it, doesn't matter. It just matters that it went from nothing to something. So I need to oppose that. I'm getting more, and I'm getting more in which direction out of the page. So I need to make, so this problem, ironically, ends up being the same solution as the last problem. Because I need to make more that cancel out. And so yeah, we still get a current this way. And we can see why we get the same answer. We changed two things. Previously I went from a field to no field. Here I went from no field to a field. Previously I had out into the page. Here I have out of the page. So double negative gets me back where I started. I wouldn't recommend trying to memorize these because that's just a nightmare. Maybe that's easy enough. I don't know. That sounds like awful. All right, this next picture I'm going to show you all is going to be really intimidating. And I'm going to let you know I'm not going to have one that's crazy looking on the test. So before I even show you the picture, and you're going to be like, whoa, that's crazy. I haven't seen one that crazy before. You're not going to see one that's crazy. I purposely picked a crazy one because I thought it was interesting. But you're not going to see one like this. It's just good practice. All right, so here's a crazy looking circuit with a bunch of resistors. And the question here isn't even find the net resistance. With this crazy, again, I'm not going to show you a circuit this crazy, but it's really good practice to kind of show which ones are in series and parallel, is to give a more ridiculous one and highlight what makes it series, what makes it parallel. So that's the question here, just which are in series, which are in parallel. If you had to reduce this to a single resistor, what could you start with? And you know, it's like one of those puzzles where they say, how many squares can you find in the following image? I'll tell you all, there's 3 things that we could start with. There's 3 combinations. See if you can find all 3 of them. I'll give you all a moment. It's like a nice little puzzle. 3 different combinations that you can make to start off with. And you can start with any one. Two of them are in parallel, one's in series. All right, so what did y'all spot? Yeah, sure.
1, 2, is that 9? Or G?
1, 2, and 9?
And 5.
Ooh, okay.
Those are all parallel.
Okay. Let's check that one. Let's check that one. So the rule for parallel is that they have to share the same wire. So I should be able to get from R1. On this side of R1, I should be able to get to all the other resistors without going through another resistor. So yes, I can get to R1, I can get to R2, I can get to R9, but I can't quite get to R4. So that knocks out that one, but let's check R. So those all share the same wire. And then the other side also needs to share the same wire. So I need to be able to get from this end to the other ones. And unfortunately, I can only get to that one. But that's great. That's like, this is a good opportunity. That one is tricky because we're tempted to think that these are all parallel to each other. Because they technically, visually, they look parallel. But parallel is the hardest one to identify. Parallel is the hardest one to identify depending on the circuit. It all comes down to that I can get, they share the same wire. That's the best kind of thing I can think of. And that means they have the same voltage across them. That means they have the same voltage because they share the same top and the bottom. Junctions don't matter. So these ones we can combine as parallel. All right, what's our next one? Yeah. Oh yeah, yes. R6 and 7, let's check that one. Series or parallel? Parallel. So we start on this side, we should be able to get to R6 on that side, awesome. And then we start on this side, and yep, there we go. So these are also parallel. Awesome, awesome. So we got our 2 parallel, which are honestly the hardest ones. Nice work, yeah. Yes, that's our series. Series is the nice one. Series is nice. Literally, they have no junction between them. That's it. That's the only rule for series. No junction between them. The wire doesn't split. If the wire splits at all, not series. Every other circuit. So, at this point, you could do all of, like, you could combine R1 and 2, you could combine R4 and R5, you could combine R6 and R7, make a new circuit, and then go from there. And in fact, that's what we'll do, but a little simplified because I didn't want to start from here because this is disgusting. Like, this is gross. I'm not going to, this is too crazy. This one's also fairly involved, but I'm not going to ask, find the current through R45. That would be a free response problem. Even that was like beyond what I wanted to even ask on the previous one because it takes a lot of time. Find the net resistance. So this is going to be a lot of picture drawing. But you're not going to have to work backwards. You don't even need to know if their voltage is the same or whatever. So, same question to y'all. Which ones can I combine? And we're going to keep doing it and doing it. It gets simpler and simpler the more you combine. So what would you like to combine? Yeah. Sure. Those are in series. And there's one more we can combine if we'd like. Yeah. Beautiful. They're in series as well, so it's not too bad. Now, if I do give a problem like this, I will also make it, I'll just say they all have a resistance of 2, because I don't want to have this bajillion many numbers on it. So in this problem, that is not the case. So we'll do R4, 5 plus R6, 7, and it's not pleasant. 2, 8, 5 plus 45, 95. Again, I'll give nice 2. I'll say like they have a resistance of 2 or 3. I don't want you all to have to be adding a bunch of gross numbers together if I do ask one like this. So that's 330.95. And then R12 plus R3 equals 7, I'll write it out. 16.67 plus 63 equals 79.67. Even though I'm fairly confident in that, I've made enough stupid mistakes in my life that I'm still going to plug it into the calculator. Good job, me. All right, so we can generate our new circuit. Boom, there's our new resistor there. That's R1, 2, 3. We still have R9 chilling right there. We still have R8. That's a hideous resistor. R8 chilling right there. R4, 5, 6, 7. Again, even this one's got just the numbers are gross. Okay, what do you want to combine now? Sure.
This one and the last one
Mm-hmm.
was resistors that were in series, but there was like a corner, like a bend.
Yeah, it's a great question.
So if you're gonna draw it out, simplify it, does it matter? Like, where do you put the resistor?
That's a great question. So the question was, where should I? In this case, there was a bend here. Should I put the resistor here, or should I put it here, or? The beautiful answer is it doesn't matter.
Okay.
Because the bend means absolutely nothing. The bend that's a great question. And the rationale is we can put it anywhere on here because current is the same everywhere on there. Honestly, as far as we are concerned, those kind of wires don't even, if we could make those wires infinitely short, we would, to show that they don't actually matter, or we can make them infinitely long. The wires themselves, the only thing that matters is kind of where the junctions are and where the resistors are located relative to those junctions. Yeah, it's a great question. Because you see these bends, and does that mean I have to bend? Nope. I like that. All right, so now we're going to combine these two. So we previously combined these two. They were in series. This one's in parallel. At this point, I'm not going to keep plugging in the numbers. I'm just going to kind of mention that you're going to R4, 5, 6, 7 plus 1 over R9 equals R4, 5, 6, 7, 9. So you'd combine those. So at this point, I'm just going to draw the pictures. I'm not going to do the math because these numbers are not pleasant and it doesn't come out it's just not worth the effort. Again, on the final, I'm not going to give you 63, 77, 50. It will literally be, they all have a value of 3. And easy. That way when you're adding them, 3 plus 3 equals 6. Stuff you can do in your head. Or even when you have to do the dividing stuff, it won't be as bad. 1 over 3 plus 1 over 3, and it won't be an awful number. Try to make your life efficient. At the end of the day, I'm not testing how many buttons you can push on your calculator. So, just to kind of show what's going to happen after this, which ones we would combine, because I do think that part is useful. Actually, I don't care about all that. I'm just going to copy, I'll copy this one so we can see the next step that we do relative to the last step. So at this point, I'm just going to show what would get combined in. So we combined those two. Fantastic. Good job, us. We got R1, 2, 3 right there. R8 is still chilling right here. We just combined these, so they make a new one. R4, 5, 6, 7, 9. R1, 2, 3. At this point, we will combine these. These are in series. We end up with R1, 2, 3 in parallel with R4. I'm not going to put the commas because that's a lot of commas. And finally, those are in parallel. My recommendation is if you're uncertain on these and you want to practice the one that was 1, 2, 3, 4, 5, 6, 7, 8, 9. Practice the one that was on the last test. Practice the one that was on the last test without looking at the solutions. That's about the level of difficulty you could expect in terms of what to combine where. Though that one did have different numbers, but again, at the end of the day, the skill that's most important is do you know which should get combined when, as far as how to combine them, pretty straightforward. Series, add, parallel, do the 1 over plus 1 over plus 1 over. Capacitors follow the opposite rules. So I will remind you all that if they're capacitors, there was a problem on the last, I believe there was a problem, I'm fairly confident there's a problem on the last test where I had capacitors in different combinations. Okay, I'm getting at least 8 nods, so unless it was just so traumatic that, let's just quickly, I'll just make up one real quick, just to make certain. If I have a capacitor, so the rules are the same as far as identifying series and parallel. So if I have 2 like this, and I have 2 like this, and I say combine these, and I call it C1, C2, C3, C4, you still do the same thing. Combine what you can first. The only thing that differs here, so this next step, these are in series, these are in series. So again, that hasn't changed. But when I get C12, series for capacitors obeys the opposite rules. Where you do the gross math for series, same thing here, we're going to do the gross math for series. And for parallel, they do the nice math. So you do just need to remember that little caveat. So this will simplify to this, C12, C34, and when they're in parallel, you just add them. It's really nice. So they're the opposite of niceness with resistors. Resistors, series, add, life is good. Series, parallel, gross. Capacitors, series, gross. Capacitors in parallel, nice. I don't know. How helpful that was. All right. So, do you need to remember that and expect something like that? Again, a rule of thumb, if I'm covering this stuff now, you can almost guarantee there's a problem like it on the final. It's always a good rule whenever any professor, I think, does a review. Otherwise, why are they wasting the time? All right. This one is a very simple problem, but one that I expect if I didn't review it would make mistakes on. I have -3 nanocoulombs of charge. How many extra charges do I have, and are they protons or neutrons? The math here is incredibly simple. So I'll let you all think, see if you can figure out how to solve this. The good news is, if you didn't know how to solve it before today, you'll now be reminded and you'll be good to go. So there's a couple key concepts here at play. One of them is everything is made of electrons and protons. Everything that has mass. I should clarify, light is not. But everything that has mass is electrons and protons. And so if you have a charge, you have an extra of something. Everything else canceled out. If I have 5 protons and 5 electrons, those cancel out, you get a net charge of 0. The second you get any charge, it's not 0, you have an extra of something, and it becomes very simple. I'll write down the equation for it. The equation, in my opinion, while useful, I think maybe end up confusing people, but it's a kind of a catch-22 where it helps some people, confuse some people. This term here is the number of extra charges. I mean, take the example I just gave you. If the number of protons is 5 and the number of electrons is 5, 5 minus 5 is 0, net charge is 0. So you can use this equation, that'll get you there if you're stuck, as long as you remember that that's the extra charges. Or you can just remember if I have extras, okay, it's going to be one or the other, protons or electrons. These are negatives, so which are they? Electrons, spot on. So we have extra electrons. At the end of the day, the question is, if I have this much charge, 3.5 times 10 to the minus 9, that's nanocoulombs. How many electrons do I need to make that happen? You just divide by the charge of an electron. Take the net charge divided by the charge of an electron. That's how many electrons get you there. That's the reason you have it, is you have this many extra. Each one's contributing 1.6 times 10 to the minus 19. It's kind of like that question with the elephants. How many elephants do I need to get to this much mass? It's going to be a big number. Electrons are tiny. Ugh. And depending on whether or not your calculator is in scientific mode or not, you may have to count some zeros. Mine's not, so I'm going to count some zeros. You know what? I'll write out my gross number, but I'm going to guarantee you that I will not. 1, 2, 3, 4, 5, 6. That's disgusting. I'm not going to put that as an answer on the test because that's stupid. We have scientific notation for a reason, but I wrote this number just to make a point of how you convert to scientific notation in case there's any ambiguity there. You see how many times I move the decimal? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. That's my answer. 2.1875 times 10 to the 10 extra electrons. So you can either remember how to convert it, or there's ways to convert, put your calculator into scientific mode. Great thing for you all to figure out how to do if you don't know how to do that already. Counting zeros sucks. Like, I don't want to do that. But it was good actually. All right. I mean, that's all my problems. Look at that. Wow. Look at my guesstimating. It took exactly an hour. Crazy. At this point, I'm gonna just chuck in one quick ratio problem. And then if there's any other problems you all want me to do, I will gladly do them, like kind of quick ones. Otherwise, I'll continue to make up problems. Makes it. So I have a battery with a voltage of 3 volts. What happens to the current if I double the voltage? We'll connect it to a resistor. The assumption is to connect it to the resistor. So, there's always the mathematical way to solve this. There is also the conceptual way to solve this. Ooh, there's my pen. So, we do have to remember that V equals IR. With that in mind, see if you all can get the answer. There's basically one of two answers I expect people to go for. I expect people to either think that the current will double or the current will half. And it all just comes down to either conceptual or mathematical understanding. Both will get you there. Conceptual is quicker if you know it, but harder to have that expertise. Mathematical just takes a little more time. So if we remember, voltage is like height. So if I double the height, my thing's going to roll down twice as fast. So that's the conceptual, get there really quick kind of answer. There's no squareds or anything in this equation. If you see squareds, then whatever happens, you need a square. I'll actually do a ratio problem right after this with that, because I think also people will get hung up on that one. But, so if I double the height, I'm doubling how fast. So the quick answer is it doubles. I'm doubling the height, so my current better double. I'm doubling the thing that's making the current happen. So, for example, if I said that I1 is my new one, it would be 2 times the original. Okay, great. That's one way of doing it. The other way is, I have my original equation here, and we call that I naught and R naught. And I'm going to write my new equation here, 2V equals I1 times R naught. And something you can do with these equations that people don't realize is you can divide them by each other. You're allowed. You can divide equations by each other. So I just bam, bam, which results in V over 2V equals I naught R naught over I1 R naught. Cancel out all the things that you can cancel out. You get 1/2 equals I naught over I1. And you may be like, whoa, 1/2, that's not the answer. Well, that's because we have to solve for it in the way that it's shown. We need to get it in terms of I1. So we kick the I1 over. So I1 times 1/2 equals I naught. I1 equals 2 I naught. We get the same answer. There is many ways to do ratio problems. This is one way, tried and true. Put what changes, divide the two equations, solve it out. Great, that's one way. Another way is you brute force it and you make up numbers. Another way you can do ratio problems is literally make up numbers. All right, so let's do that. Let's make up some numbers. Let's say, I already gave you the voltage, so we don't really want to make that up. Let's make up that the resistance is 1. I highly recommend making up numbers that are easy. So let's just pretend that the resistance is 1. We're allowed. So 3 equals the current times 1. All right, what's my original current equal? 3. What a nice answer. Now, let's go ahead and get our new current. We know the voltage is going to double, so it'll be 2 times 3, that's 6. So 6 equals I1. My resistance is still 1. I have to use the same resistor, it didn't change. So what's my new current? 6. Oh look, it's double. That's another way you can do ratio problems, just make up numbers. Be consistent though. If I make up the resistance and I say it's 1 ohms, if the new situation is the same resistance, it better stay 1 ohms. So that's the only trick. Lots of things. All right, real quick, last thing I want to do before I take any things is I want to give an example. This is an important problem to be able to do, and I expect a lot of people are going to mess it up. But we've seen it before. I say a lot of people. We'll see. I'll be optimistic. I hope a lot of people get it right. 2 charges are a certain distance apart. What happens to the force if I quadruple? So that's making it 4 times bigger. If I quadruple the distance. I'm going to save you all a bit of time. I'm going to give you the equation for this. And I'm going to show you another way. This is kind of a simple way. What happens if I quadruple the distance? Will my force be 4 times bigger? Will it be 1/4 bigger? Will it be something else? This kind of ratio problem is really good because it's got a squared. And a lot of people forget about that squared. So our original is there. Our new one, this one's a little simpler to work with. What I like to do is you can just put the change right in front of it. And that's the key right there. Whatever you do to the variable has to also be squared. Again, you can make up numbers to prove this to yourself. If the distance previously was 1, 1 squared is 1. If my new distance is 4 times bigger, 4 squared is 16. You have to square whatever happens. So KQ1, Q2 over 16R squared. We pull that 16 to the front. It's in the bottom. So my new force is 1/16 the original. You have to be careful with these ones. Again, there's a couple of these. I think one of these on test 1. I think. Certainly it would have shown up in a quiz. It was either in a quiz or a test for sure. Make certain you can do this. Make certain you remember that if you have a squared and that variable changes, you have to square that change. If it's in the denominator, it stays in the denominator. If it's in the numerator, it stays in the numerator. So in this case, that 4 was on the bottom. We squared it to 16. When we pull that to the front, that 16 needs to be on the bottom. Okay. That's kind of the most critical problems I can think of, the most likely that mistakes will happen. Only other thing, remember that protons and electrons do opposite stuff. So, is there anything that you all would like me to do in the last 10 minutes? Yeah.
What do you think is the most likely thing that a lot of people are going to get wrong for the last 2 chapters, the light, the optics?
Yes, that's a good question. What's the most likely thing I expect people to get wrong? If I give a problem like this, where I say, and I'm not going to solve this whole problem because I don't need to make the point. The math is pretty simple. A diverging lens has a focal length of 3 meters. If I put an object 2 meters away, what is the image distance? So super straightforward problem. The mistake I expect, if people make a mistake on this problem, it's going to be the following. When we do a step 1 and we write down our givens, we have focal length and we have object distance. So that's pretty straightforward. And our focal length is 3 and our object distance is 2. I'm expecting people to forget, not expecting. If they make a mistake, it's because they forget that a diverging lens, f is negative. Diverging lens, f is negative. That was one of those rules that we had written down. It's like, that's the only rule you need to remember as far as positives and negatives. Anything else will come out from the answer. So a diverging lens, f is negative. And I'll also put this on here. You're going to get an answer for this problem. You will get a DI that's negative. You can do the math and prove that to yourself. I mean, I'll just quickly work through this. This problem's pretty straightforward. DI equals question mark 3, 1 over F equals 1 over DO plus 1 over DI. If I plug in, and then if I quickly solve for DI, again, you can prove this to yourself. It's 1 over F minus 1 over DO. If I just plug in those numbers, I get 1 over negative 3 minus 1 over 2. Comes out to something I'm not going to even try to guess. Probably 3/2 or 2/3, something like that. I'm not going to try to guess which because I'll get it wrong. Yeah, it wasn't even close. Close. Negative 1.2 meters. So my DI is negative 1.2 meters, and this negative means it's on the same. If you get a negative DI, image is on left side of mirror, or lens, left of lens. Positive DI, right side. Negative DI, left side. Kind of matches what you'd expect. Positive x-axis, negative x-axis. So those couple rules will be helpful to remember. A negative DI means something different than a positive DI. It doesn't tell you whether it's right side up or upside down. I mean, you have to do an extra step to figure out if it's right side up or upside down. But that negative tells you that it's to the left of the lens. Left of the lens. Positive DI tells you it's to the right of the lens. So, a couple things here. That's a good one to keep in mind. Otherwise, the only other thing I expect people to make a mistake on is ratio. We've done stuff with wavelength and frequency, recognizing that as wavelength goes up, frequency goes down, and just not mixing it up. So if my frequency doubles, my wavelength halves. If my frequency quadruples, my wavelength quarters. So on and so forth. Yeah, that's a good question. So those are the most common ones I expect. People make a mistake on. Anything else? All right, I mean, pretty much good for me. I mean, we got 7 minutes left. If you want, come on up. I'll be happy to solve any kind of problem you want me to do in the next 7 minutes or whatever. If you want to come up, have any questions. But instead of going to the end, I think we'll just call it here, and you can come on up, and I'll stay here till normal class time ends, and after that, if we, as I usually do. And I'll post this. Always do. So this completed one will get posted right now. So use the study, go through your quizzes, go through your tests, go through the problem sets, basically same old stuff to study. And that's it, y'all. It's our last class. Next time I see you, we'll be sitting all together. This room will be so much fuller, so much warmer. And then that'll be it. Our time together will depart. Be just a fond memory, hopefully fond. Oh, please do that student perception of instructor. It means the world to me. If you don't do it, my feelings won't be hurt. I'll never know.
Thank you.
Yeah, thanks. I appreciate it. And yeah, if there's anything I can help you all with,